Hello everyone. This week we're going to look at electric field with more than one charge. So remember from last week, electric field is a vector. That means you do have to deal with direction. So when there are more than one charge on the system, you have to deal with that too. Now first, let's look at what those electric field will actually look like when you have more than one charge. From last week, we have the electric field for one charge, which looks like this, from positive charge or negative charge. So remember, positive charge has electric field that are going away, and negative charge has electric fields that are going into it. Okay, so what if we have a double positive charge? That means positive charge times two proton in close proximity. So what would the electric field look like? Now, so we do have a simulator to simulate something like that. So in this picture right here, you are going to see exactly two proton with the electric field. I can actually make them go further or closer together. So if you look at each of the charge individually, it looks like a positive charge with all the electric field going away from it. Now, but something in the middle is interesting. So there is actually this line right here that is in the, oops, I think I touched something. Let me bring it back down to this level, which is like down here. There we go. Okay, so now we're going to try to draw it. So as you can see, the arrows are going into going away from each of the charges, but when they meet in the middle, they kind of push away each other. So how do we represent them in our notes? So we will do it in this way. So there's going to be a line. If these two charges are exactly the same magnitude, that line will be right in the middle. So the electric field going away from each charge is going to look like something like this. So remember, all the arrows has to go away from a positive charge. So something like that. And here will be something like this. Okay, so, and then on the other side, it should be exactly the same thing. So let me just really quickly draw that right here. So all the field lines cannot cross. Number one, right? They cannot cross. And number two, they are kind of moving away from each other. Okay, now remember, what does that mean? What does the electric field line mean? These are, so let's say you have a positive charge, right? Those are the directions that the positive charge will go. So if you have this little positive proton, and then you want to bring it, like, let's say close to here, and what will happen is it will get repelled, it will get pushed up. If you put it like here, what happened? It will follow this electric field line. If you put it on the right hand side, what happened? It will go to the right. If you put it right in the middle, what happened? It will kind of stay in the middle because it's being pushed from two equal force on two equal side, right? So in the middle, there's nothing. Okay, so next one. So now for negative charge, it will be the same thing, except that I reverse the polarity. So now these two are negative charge. Individually, you can see that the arrows are pointing into the charges, and in the middle there is a line where things are going straight also. So let's represent that in our picture. So right here, so negative charge, let's use red for negative charge, and so that there's also this line if the two charges are exactly the same magnitude, right? So two negative charge with the same magnitude will look something like this. So this goes in, so all the arrow goes in. It's actually a lot like the picture that we have for two positive charge, except that all the arrows should be going in, not away. Okay, so I can draw all of them first. So let's make sure the numbers are the same. There you go. And make sure all the arrows are pointing into the negative charge. Remember, they have to be pointing in because those electric field line are the direction that a positive charge would go. So if you have a positive test charge and you put it right here, what happened? They will follow the line and go up. If you put it, let's say over here on the lower right hand corner, it will go up and attach to that negative charge, which makes sense. Positive charge should be attracted by a negative charge, right? So now note that the electric field lines point in opposition to each other. In both cases, they either pointing both away or both into, so they are pointing in opposition to each other, because this electric field is a force field, it's a vector. So when multiple fields overlap, we simply add them up as a vector. So we'll add them up as a vector, and you will see how that is going to be something that you have done, like adding forces and adding speed later on when you have two charge in the same space. Okay, so now let's try two opposite charge. So opposite charge, meaning that, let's say you have one proton and one electron. So if you have one proton and one electron, so in here, that is actually called a dipole, which is one positive charge. Now this is a 3D rendering, so it looks really messy. I'm just going to reduce it down to a 2D picture so that you can own. So in real life, it's actually 3D. But for easy to draw, we just draw the 2D version, and you can see right now. So what happened is the charge, which one do you think is the positive one? Just looking at the electric field. It's the one that has all the arrow going away from it, right? Which is the left-hand side one. That's the positive one. And the negative one has all the arrow going into it. Now, but you can see some of these arrows are actually, in the middle is pointing away from the positive and into the negative. Okay, so in our note, let's represent that. So now we no longer have that middle line in between where you don't have anything. So instead we have like these. So it's pointing away from the positive and into the negative like this, right? Away from positive into the negative. So the direction away from positive into the negative. And let's do one in here, do one in here, do one away, do one in here, do one in here, do one away. And let's match the number. If they are the same magnitude, the number should match. So go in, go in, go in, go in, go in. There we go. So every single line should be accounted for. Okay, so when two fields interact, in this case, they collect to each other if they are opposite charge. Okay, so if you have two opposite charge, one positive, one negative, the electric field should be collected to each other. So in case, again, just one last time to remember, the electric field line is basically what happened to a positive charge if you put it near the system. So what happened to a positive charge if you put it like right here? It will go to the right hand side. Why? Because it's repelled by the one on the left, which is positive, and it's attracted by the one on the right. So together it pulls it to the right hand side. If you put it right here, it will first be repelled by the positive charge, so it will go up a little bit, and then it's once in the middle, it started to feel the attraction force from the negative charge, so it goes like that, right? Okay, so now let's get some 2D picture, a 2D question done then. Okay, so what is the strength of a electric field midway between two charges that are one positive, one negative? Now remember the equation for electric field from last day, so we're going to still use that equation today. Nothing has changed, so it's KQ over R squared, except that we don't put any sign on the Q. Okay, so absolute value on the Q. So remember, direction will be given by just the picture, and you need to draw a picture in order to know that. The equation itself is going to help you find the magnitude. Okay, so let's draw the situation. First, there's a positive charge. It's 2 microcoulomb. Microcoulomb is times 10 to the negative 6. Okay, now we have a negative charge right here, which is negative 4 microcoulomb. Negative 4 microcoulomb, which is over there. And let's say now these two charge is 0.6 meters apart, and we want to find the strength of the electric field midway, that means right in the middle between these two. So midway is in the middle, so that's 0.3 away from the left, 0.3 away from the right. Okay, so now, so we don't kind of leave that 0.6, let's say 0.3. So it's 0.3, 0.3, right in the middle. Okay, there we go. Now, so what is the electric field? Okay, at that point. Now this point has nothing in it. It's just a point. It's called point P. Okay, so first of all, positive charge looks like what? Positive charge looks like this, right? So it looks like this with all its arrows going away from it. So right there. Now, so if you imagine that we draw all of those on our positive charge, so I'm overlaying them right now. Hopefully you can see it. Okay, so at point P, at this point there, point P, which direction is the electric field from this 2 coulomb positive charge? Which direction? Now, if I can move slowly over there, you can see that the arrow that goes through point P is pointing to the right hand side. Okay, so remember, these electric fields are not disappearing because I don't draw it there. I mean, technically speaking, that electric field is extending to space forever and ever and ever. It just gets weaker as you extend it, right? So technically speaking, it's like that with all the arrows that are extended, right? So if you imagine taking this whole thing and placing it over there, over top of ours, then you can see the electric field from the 2 microcoulomb positive charge that's going through point P is going to the right. Okay? Hopefully that's enough to convince you of that. Now I'm going to label the 2 charge. I'm going to give them a name. The name, the charge right there is called EA, and this charge is called B. And so I have my first electric field. My first electric field is a electric field that points to the right hand side. And where does that come from? It comes from charge A. So I'm going to call it electric field A at point P. Now, how do I find electric field A? Well, electric field A is easy. Electric field A is K, the charge of A, which we have right there, charge of A right there, over the distance to A. Now, the distance to A is right here. So that would be 0.3 meter square. So KQ over R square. Okay, so you know what? I'm just going to put R first. RA and then square. Okay. All right. Now I'm going to put the numbers in. So the number is K. K is 9 times 10 to the 9. It will only put that this one time. 2 microcoulomb. Micro is times 10 to the negative 6. And then we have the radius square. So the radius is 0.3 meters. And make sure we square that. And you get a number. Okay, so you get a number for this. Now, what is that number? What is that number? So if you put all of these in the calculator, you're going to get, I think, 200,000 rounding. Okay, 200,000 electric field, which is Newton per coulomb. That's the unit. Direction. What direction is electric field A? Well, that's pointing to the right-hand side, right? Okay, so right-hand side. So you put right-hand side. So the diagram tells us that it goes to the right-hand side. There we go. Okay, so that's one down, one to go. So we have to now deal with electric field B. Now, electric field B is a negative charge, though. A negative charge has all its electric field pointing into it, right? So imagine that we have a negative charge in here. The electric field should be going into the charge like that, right? So into it, into it, into it. Now, let's say I make that one on the left much longer so that you can see what happened. And okay, so then I take this whole thing and I overlay it over here. So now you can see from charge B at the point P, which is on the left of it, the electric field from charge B is also pointing to the right. So that means we have to draw another electric field that's also pointing to the right hand side. In addition to that electric field A, we have this electric field B that's also pointing to the right hand side. It just happens that they are perfectly situated over there. So now we can try to calculate electric field B. Okay, so electric field B is the same equation as electric field A, and yet, yes, we don't put the negative sign in it. So there will be K, and the electric field is 4 microcoulomb. So 4 times 10 to the negative 6. Remember, no negative sign. Over the radius square, which is 0.3. And we square that. So in the calculator, it's going to be double of what we have before, because the only number that changes the charge from 2 microcoulomb to 4 microcoulomb. So it's going to be 400,000. 400,000 Newton per coulomb. And it's also pointing to the right hand side. So therefore, even though the electric field is coming from 2 different charge with opposite sign, but at location B, both of those two electric field points to the right hand side. So when you have two vectors that point to the right hand side, what should you be doing? Adding them, right? If one points to the right hand side, the other one points to the left hand side, then you subtract the bigger one by the smaller one and then use the bigger one's direction. So the total electric field, right? So we say the total electric field at point P is then equal to EA plus EB, which is 600,000 Newton per Coulomb. So it's not always adding or always subtracting. It depends on the direction in your diagram. There are many situations where you will need to subtract them. It's just that in this case, because, well, you pick the location in the middle, so we have one adding, one subtracting. I could have picked other locations where, so for example, let's see if you understand this. What if I pick P as like here? Like I'm highlighting it right now. So what if P is over here? What happened? Then the electric field from charge B is actually going into charge B. So then EB will be this way. But then the electric field from charge A, this one, is going away from A. So by the time it gets to B, it'll be pointing this way, right? So therefore, field A and field B will actually be opposite. And then in this case, you get electric field A and then get electric field B and see which one's bigger. And then bigger one subtract by the smaller one, and the direction at the end should be the one with the bigger electric field. Now, unless they're exactly the same, there are a slight situation where they could be exactly the same, and then they cancel perfectly, and then you will say, okay, the electric field in that location is perfectly zero. It actually could happen, okay? But it can only happen, I think, on the other side, on the side next to the A, because this charge right here is the stronger charge, is -4. The other one is only +2. So you have to be closer to the weaker one in order for you to have a stronger effect from the weaker one to cancel out the stronger one, right? So on this side, there might be a chance to get a electric field of 0 when you add them up. Not on the other side. Okay, so now let's try another example. Example 2. So two charge, this time they're both positive. Okay, so they're both positive. And so positive charge number 1, positive charge number 2, they are 0.4 meters apart. And they're both 5.25 microcoulomb. So that is exactly the same. So 5.25 microcoulomb. And what is the strength of the electric field between them at a point 0.1 meters away from the first charge? Okay, so this time we are not in the middle. We are right here. So this location is 0.1 meters from the first charge. So 0.1 meter and 0.3 meters from the second charge. Okay, now again, we're going to label them. Charge 1, charge 2, charge A, charge B, whatever you want it to be, right? So let's say this time we use charge 1, charge 2. So charge 1 is on the left, charge 2 is on the right. Okay, so we have a label. Now, let's see. Remember, electric field from positive charge is going always away from it. So from charge 1, the electric field going through this point P, which is an arbitrary point that the question picked, happens to be going to the right-hand side. So let's draw that. So charge 1 happens to be like that. So this is going to be our E1. Is the electric field at point P due to charge 1. I'm going to put charge 2, allow me to change it to a different color so that you can see. I'm going to have a charge 2 of a purple color. There you go. Okay. Now, so for charge 2 has always electric field going like away, right? Like that. So by the time it gets to point P, well, it goes to the left-hand side. So I only want the part that goes to point P. So it goes to the left-hand side. And then, there we go. So left-hand side at point P. So this is going to be electric field 2. Okay, so electric field 1, electric field 2. Now, why do I draw the electric field 2 smaller? Look at the arrow. Look at the arrow between the field 1 and field 2. I drew it smaller on purpose. Because if you have to remember, these two charges are equal sign, and you are closer to the first one on the left. So therefore, is effectively stronger. It's like you have like a fire in here, another fire in here, and you're closer to this fire, then you will feel the heat from this fire stronger than the heat from the other fire, right? Electric field is a lot like, heat and temperature sometimes. You have to get closer to actually feel the effect. So therefore, I expected E1 to be bigger and E2 to be smaller. So my final answer should be pointing to the right hand side at the end, even though the number doesn't have a direction. Now, think about it. If you get E1 and E2 right now, you will realize that they have both positive number. So you think, if you just look at the number, you think you need to add them. But no, they're pointing in different direction. E1 is going to be K, Q1, which is 5.25 times 10 to the negative 6. And you have to divide by the distance, which is 0.1 meter. And you need to remember to square it. Now, that will give you a number, right? That will give you a number. Now, this number turns out to be, I think 4,725,000 Newton per Coulomb. And which direction does that go? Right hand side, right? It's going to the right hand side. Look at that. Now, you have electric field 2. So, same thing. K, Q1. This part is actually exactly the same. K, Q1, Q2. The only thing different is the distance, which is 0.3. So 0.3 instead, square. So this will be a smaller value because you're dividing by a larger number. And that turns out to be 525,000 only Newton per Coulomb. But which direction is this pointing at? We'll go and look back at this. It's to the left hand side, unfortunately. So therefore, we have that. One is going to the right, the other one is going to the left. Even though they're both positive, we cannot add them. We have to subtract them simply because one is to the right, the other one is to the left. So in this situation, the two charges are opposite, but we end up adding them. In this situation, both charges are the same, but we end up subtracting them. See how useless sign would be in this case? That's the reason why we don't use any sign on the equation. The sign makes no sense. If we use positive and negative sign, the first question should have been positive on this one and negative on the negative charge answer. But we end up having to actually add them, right? And in this question number 2, both charges are positive. So we have two positive numbers, but we ended up having to subtract them. So the sign makes no sense. That's why we don't care about the sign in the equation. We just care about the magnitude, and then we use a picture. The picture with the diagram tell us if we should be adding or subtracting. So in this case, let's finish it. So the E total is, so you have to subtract the two value. So it will be 420,000 at the end. 4,200,000 at the end. And is which side is winning? The right hand side. The right hand side was much bigger to begin with. So it wins out in this situation. All right. Okay. So now let's tackle the B's. Okay. So let's tackle the B's. So the B's is when the charges are not on a line, but at an angle to each other. So we want to find the magnitude and direction of the electric field at point P. Now I apologize. I think the printer was having like some trouble looking at this. By point P, I actually mean this. I don't know what on earth that is. Okay? Because if it's on that location, you will actually cry. And also, I think the units for these charges are not well put out. It's actually microcoulomb, just like the other. This is 8 microcoulomb. And that's 12 microcoulomb. So we will start by, now after we fix all the numbers, so we'll start by drawing the electric field at point P, just like the other two questions. Now these, I think the one in the bottom is actually a negative charge. So I think I missed that. So this one, the 8 microcoulomb, is a negative 8 microcoulomb. So it's actually a negative charge. Yeah, we don't actually need that number in the equation, but remember, we do need that in the diagram, right? So for the 12 microcoulomb is a positive charge. The electric field should be going away, away, away. So the one that's pointing toward P is going to the bottom, right? It's going to the south. We can say that like that. Okay, so let's label it. Let's say this is A, this is charge B, and we now have a first vector, which is this one right here. So this is the electric field at point P due to charge A, the one that is 12 microcoulomb. Okay, so moving on. Now, so we have this one that points toward the south. And now for charge B. Now, charge B is a negative charge, so all the electric field should be pointing into it like that, right? So the one that goes through charge P, go through point P should be going this way and going into charge B, which is pointing to the right hand side. So I don't have to draw that giant arrow, so let me just replace it with something slightly smaller. You know what, just to make it like very obvious, let's do that, right? Let's do this. So let's make the charge very obvious. So this is going to be our electric field B, okay? And it's going to the right hand side. It's going into the charge B, right? So going to the right hand side. Now, so what we need to do right now is to just get electric field A and B separately with the electric field equation and try to add them or subtract them depending on their directions. Now, because their direction is actually not opposite to each other, we will need to use a vector diagram like a triangle to actually do it. So first of all, let's get to charge A. So charge A, so we have a lot of space. You know what? Let's not squeeze ourselves. Now charge A. So charge A is going to be K. So the first charge is 12 microcoulomb, which is negative times 10 to negative 6, over distance 6 meter. 6 meter is the distance from charge A. So 6 square, and that is going to give you 3,000 Newton per Coulomb, and it's going to the south. Okay, so it's going south. Now, so that's the direction. And then charge B. So charge B is K Q1. Now negative 8 microcoulomb, but I don't care about the negative, and we're going to put it over the distance, which is 4.5 meter square, and that is going to give us 3,556. So it turns out to be 3,556 Newton per Coulomb, and this one is going to the east. Okay, so these two are not the same direction. They're also not exactly opposite, so it doesn't work as just a direct addition or subtraction. So what we need to do instead is draw out those two vectors, which is actually not that hard. So we start with the blue one, which is going to the south, and it's 3,000. So this way, so this is going to be our electric field A. And how big is that? Is 3,000. Okay, so that's the magnitude. And then we have our electric field B, which is going to the east, which is this way, and it's slightly bigger. It's not a lot bigger. I mean, it's 3,000 versus 3,556. So, not a lot bigger. This is electric field B, and it's going that way. So our resultant electric field, our final electric field, if we add them together, should be going this way, right? Tip to tail, from the beginning to the finish, this way. That is our total electric field at the end, ladies and gentlemen, right? So to get that, easy. I mean, at this time, how many times have we done a vector diagram like this where we had to figure out the angle and the magnitude of the resultant? Too many times, right? So we are going to Pythagoras the magnitude. So it will be 3,000 square plus 3,556 square root, the whole thing. If you add them together, it's going to be 4,652 Newton per Coulomb. And tangent for the angle, of course. So tangent theta is equal to, I usually do opposite over adjacent. So 3,556 over 3,000. And that will be 50 degree. So 50 degree. And what do we call this angle? So 50 degree east of, touching south, but it's going to the east. So east of south, 50 degree, east of south. East from south, right? There we go. So the final answer to this question is a electric field of 4,000-ish Newton per Coulomb at the end due to the two charges, and is pointing 50 degrees or so. All right, so that is the hard part, because you have to end up using the vector at diagrams to find the final things. So now the next part of the question, actually there is a part B, which is here. Suppose you put a proton in point P. Okay, suppose at point P, instead of just being a space, you put a proton in it, which is a positive charge. Now, what happened is that proton is going to get pushed by the electric field going in the same direction as the total electric field. Remember, the electric field is the direction of a positive charge movement if you have a positive charge in it, right? So at that point P, there is a electric field that goes this way, which we have determined from part A. So if there's a proton over here and it is getting pushed by this electric field, then there will also be an electric force going that way, right? There will also be an electric force. So this electric field, this total electric field, is 4,652, right, Newton per Coulomb. So how do we use that to get electric force? Well, we do have an equation to convert them. Electric field and electric force is off by a charge, the charge of a proton. There you go. So electric force is equal to electric field times charge. Oh, I have the electric field and I know the charge of a proton. So this is because we are putting a proton in there, so that's charge of a proton. Now, so the electric field times the charge of proton. Well, that's not too bad. So the electric field is 4,652 Newton per Coulomb, and the charge of a proton is 1.6 times 10 to the negative 19. That's the elementary charge. You can see why these two things together, multiply together, equals to force by just looking at the fact that your unit has dividing by charge and then you're multiplying by charge. So the only thing that's left after you divide and multiply by charge is Newton. So the rest of the equation must give you something that's in Newton, which is the force. So the force is 7.44 times 10 to the negative 16 Newton. So that's the electric force. Okay, so why do we need electric force? Because I want acceleration. And what better to give you acceleration than net force, right? There's only one force on the proton, and that's the electric force. So the electric force is the net force in this case. F net equals to ma. So if I want acceleration, I'll take that electric force and divide it by the mass of a, proton. So proton mass. So mass of a proton. Okay, so electric force is, what we just got up there, 7.44, that value, times 10 to the negative 16 Newton. And mass of a proton is 1.67 times 10 to the negative 27 kilogram. I just happen to have that memorized. Okay, so now dividing them, getting the acceleration. So the acceleration, very big number, 4.46 times 10 to the 11 meter per second square. Now, some of you might look at the acceleration and say, but Mr. Chang, that's stupidly large. Wouldn't that object get faster than the speed of light in just like a second? Yeah, that's true, but it won't stay there for like a second. It's going to get pushed away so fast that it will only spend like a fraction of a second at that location. And remember, once it starts moving away, so you're talking about like a proton that's being, I guess, forced in this environment where it's extremely close to two charge. One is going to push it away. One is trying to push it away. So like you're talking about some charge that's positive charge that's over here, and it's getting pushed away by this one. It's getting attracted by that one. So eventually it goes like this way. It's going to move away very, very quickly. So it will only spend like a very short period of time being there, a lot less than a second. And once you're far away enough, the force will decrease and your acceleration will decrease. So even if you start with an initial speed of 0, you won't get to the speed of light. You might be able to get to like 80-90% of speed of light, which is possible. I mean, in nature, that's how some particle actually, gain that kind of speed because they're very close to or near another charge that are positive or negative, and then they get attracted or repelled by it, and they gain incredible speed. Okay, so now that's it for this week's lesson, and stay safe again. I think things are opening up pretty soon. Some things are opening. Shops are opening, some restaurants and playgrounds are opening, but still, we are not completely out of this epidemics yet, right? Until the vaccine, basically. So still stay safe. Keep your distance from each other. Wash your hand often. Don't put your hand in your mouth or your nose or your eyes or your ears when you're outside before cleaning it. And I hope to see you soon. Bye, everyone.